Hi everyone, my name's Stephen. Welcome to DG STEM TV. Welcome to DG STEM DG. Welcome to DG STEM TV. Let's let's do let's do some science.
In last week's episode, we explored gravity, space, rockets, and propulsion. This time round, we're going to dive straight into an experiment exploring how these work in a little more detail.
So, in the last episode, the pressure inside the bottles forced the gas downwards out through the nozzle and the rocket upwards, and the same with the air rocket, and that creates a force called thrust. So thrust is what powered both of the rockets last week, and it's what's going to power this guy too. This is a great example of that pressure because you can see it, right? The air inside the balloon is trying to fill up the space, and the balloon plastic, this elastic's trying to shrink down, so they sort of balance each other out. But if I allow an opening here, and if the opening doesn't get too caught, what should happen is thrust is created. Hey, let's do that again, shall we?
For this experiment, you will need some string, a plastic straw, a bit of tape, and a balloon. You set it up like so, and when you're ready, let it rip. Maybe that was a poor choice of words. So now we have a total of 3 different rockets, all of which use gas for fuel, but the same force, thrust, to move forward. And all of them are constrained by gravity. Because they don't go fast or high enough to escape the Earth's gravitational pull, they fall back down to the surface.
But there is another force that has a major effect on our rockets. I'm a massive fan of old space movies, right? Where there's an astronaut up in the sky and then there's a team of like mathematicians and scientists, and they're on the ground trying to get them home because there's been some kind of malfunction or problem. And one of the best bits of all these films is usually towards the end when the shuttle is coming down through the Earth's atmosphere and you see it start to sort of judder. And then you see inside, and the astronaut, he's shaking about in his seat, or she's shaking about in her seat, and there's sweat dripping down their face, and they look out through the porthole, and they're trying to see what's going on, but then the world outside sort of turns orange and fiery, and you see outside, and there's this cone of fire around the craft, and it's shaking as it goes through the sky. I'm leaning forward in my seat, I've dropped my popcorn, I'm screaming, "Come on, man!" And then, parachute opens, and it slows down, and everything's fine. I love it. But you've got to ask the question, right? What's going on there? Why is this happening? Why is there this ball of fire around the craft? And the answer is, it's caused by this other force. It's called friction. Friction's one of my favourite forces because, well, it's kind of forgotten about sometimes. You know, it's so common, it's everywhere. But it deserves attention because it can surprise you in a lot of ways. And actually, to do just that, I have asked my good friend Kimberley to do a wee experiment for us.
Thank you, Stephen. So what I'm going to be doing is using some paper, a bottle, some long grain rice, and a chopstick or pencil to demonstrate friction. I am going to get my paper and make a funnel, and I'm going to put it into the top of the bottle and pour through the rice. I'm going to fill the bottle right to the tippy top with rice, and then I'm going to put in the chopstick or pencil and pick it up. My question to you is, do you think I can do this? Oh dear, that didn't work. Now for some appliance of science. What we need to do now is tap the bottle on the surface that you are working at. This can be quite noisy, but this will then make the rice move about in the bottle. It will compact together, which will then make a space at the top of the bottle. This is where the air is sitting. You will now need to add more rice to the bottle and tap again. This then gives the rice less room to move about, which will then mean it becomes more compact and will then produce more friction that will allow the rice to grip the chopstick, therefore allowing me to pick up the bottle. Ta-da! Looks like magic, but we know it's the power of friction. Now it's your turn. All you need is some things that can be found around the house. Some paper, a bottle, a chopstick or pencil, and some rice. Now I will pass you back to Stephen in the studio.
That was incredible. The drag created by the individual grains of rice against that chopstick lifting up that massive weight. Wow! It goes to show how surprisingly large the force of friction can get. And you might have guessed that our astronaut pals I was chatting about earlier, they are looking out of their window at a literal wall of flame created by friction. And that's it. That's mind-blowing. And you know what? It doesn't just happen in the movies.
This is footage of the UK astronaut Tim Peake returning to Earth in 2016 after his time spent in the International Space Station. And you can see the charring and burning that's happened mid-flight, causing all that scorching heat. And look at these videos of asteroid impacts. You can see the trails of debris they leave behind. It shows just how amazing the power of friction can be.
Now you might be wondering, how is friction what affected Kimberley's rice experiment and these spacecraft? They're such different events. Why are they affected by the same force? And the answer is that there are lots and lots of different types of friction. For example, static. With Kimberley's rice experiment, when two solid objects moved against each other, they weren't able to overcome the friction between them, so they stayed still or static. And then there's fluid friction, when a solid object moves through a liquid or a gas, like the spacecraft. There's lots of other types too, like there's sliding, which is just like static, except this time the force moving the object is able to overcome the friction, so the objects do move. And then there's rolling, which is when an object like a wheel or a tire rolls along the surface of a solid, like that. So you see, you don't need a spacecraft to get the feel of friction. There's lots of different things you could do. You could recreate Kimberley's experiment yourself. You could, just rub your hands together to create some sliding friction. You can slide around in your socks on a hardwood floor. And then you should ask yourself, why does it work better when I'm wearing my socks and not when I'm barefoot or when I'm wearing shoes? And why does it work better on a hardwood floor than, say, a carpet?
You can even use friction to make static electricity by rubbing a balloon on your head like my friends are doing here before sticking them onto me. You can try this at home yourself too. Think you can beat my record?
If you've ever used a pencil and an eraser, you've used friction. If you've gone down the slide or gone down the fireman's pole at a play park, you've used friction. Have you ever made the mistake, right, of going down a slide when you're just wearing shorts and then your bare skin's on the slide? If you haven't, I wouldn't recommend trying, but what do you think would happen? How would it affect the outcome? And while you're at it, what other ways does friction affect our everyday lives? What can you think of?
Think of the tyres on this 4x4. Do they need lots of friction or very little? And how have they achieved that? Then think of going down a water slide like this one. Again, do we want more or less friction? And why are water slides better than just slides, and what part does friction play in that?
So, we've discovered and we've explored how friction has a massive effect on objects in the Earth's atmosphere, right? But does it exist once you're up there, on the International Space Station or further out in space? Well, yes. When two objects rub together in space, there will be friction. It's a surface effect. It doesn't depend upon there being breathable air. But then, going back to my favourite movies and our astronaut, Tim Peake, why isn't there always a ball of fire around our spacecrafts there is friction in space? The answer to that is something we've talked about a little bit before, and it's that space is a really, really good vacuum. Not perfect, but pretty good. And what's a vacuum? A space devoid of matter, which means there's nothing in it. Now remember earlier I was saying that fluid friction exists when a solid object passes through a fluid or a gas. If there's no fluid and there's no gas, there won't be any friction.
Because of this, the moon, which is orbiting around the Earth as we mentioned last week, will stay in motion because there's no friction to slow it down.
So, if you threw a rock on Earth, it would be slowed by friction and then brought to the ground by our old buddy gravity. But if you pick that rock up, hop on a shuttle up to the International Space Station, then put on your spacesuit, go out for a wee walk, and then strap that rock to a jetpack or something similar, fire it off into the distance, it would soar on, slowed but not stopped by gravity, basically unimpeded by friction. It'd just keep going, right out of the gravitational pull of our sun, out of our solar system to the space beyond, where we're still just beginning to explore. And then inevitably it'd fall into the gravitational pull of something large enough to counter its speed, or maybe it'd just crash right into it. But who knows? And you know what? We've actually already gone and done that. Not with rocks, of course, but with space probes.
Like Voyager 1 and 2, which were both used to prove a theory of a prominent Dumfries lad named James Clerk Maxwell correct, if you remember, and which have now left the solar system altogether and are still able to transmit data despite being billions of miles away.
And what's more, they carry messages to the stars, to the whole universe, just in case anything out there finds them, saying, "Hello, we're here. 4 stars to the left, 3rd planet from the one we're orbiting. Drop in sometime for a fly cup." And you never know, someday someone might.
But of course, while friction can be useful, it can also be dangerous.
Remember our astronauts juddering in their spacecraft? They are dealing with a very real threat. If the angle of their descent is too steep, then the spacecraft could burn up. Anyone inside would be crushed. If it's too shallow, on the other hand, then the force of friction won't be enough to slow it down. And then the spacecraft will simply continue and go into orbit around the planet. So it'll go like this, round, and then come back down in a completely wrong place from where it was meant to be. And what's more, when it comes down, it certainly won't be coming in at the right angle. So the ideal re-entry trajectory is a very narrow band between these two extremes. So whenever anyone comes down from the International Space Station, a lot of maths is required to ensure that it's correct.
One space movie I particularly love is Hidden Figures, which is about Katherine Johnson and her colleagues who worked for NASA in the 60s as computers.
And that's as computers, not on computers, because she had to take all these bits of information, speed, angle, air resistance, and work it out in her head and on a bit of paper with a pencil. Because things like smartphones, iPads, laptops, they hadn't been invented yet.
She was a genius. So smart, she was able to quietly work against and ignore discrimination against those who were black and those who were female in NASA and many other organizations in the early 1960s. She worked on the Apollo 11 mission, when the first astronaut landed on the moon, and she worked on Apollo 13, which had to be aborted mid-mission due to an explosion in the spacecraft. Without her work, they wouldn't have been able to get home. I think she's iconic. Now, last episode we challenged you to send in footage of your own amazing bottle rocket experiments, and we've selected some of our favourites to share. This one had an amazing launch. See how thrust is created at the nozzle. And here you can see friction plays a big part in spinning it round. A little ingenuity helped set this one off. And these guys were maybe more excited than me at launch. Well done. Now we'd love to challenge you to film your own balloon, rocket and rice experiments and send them in. And why don't you try some variations in the experiment? For example, this was my first attempt, but what happens if I use a different balloon? Interesting results, eh? And then what if we swap strings to something thinner and adjust the height? What are the effects on friction? And what would be the ideal setup for speed and stability? I leave it to your imagination.
I hope you like friction just as much as I do now. It's truly so amazing and cool and interesting. I was so overjoyed to hear how much everyone enjoyed the first episode on propulsion, and I really hope you like this one just as much. If you want to talk to us about it, ask us questions, come join us.
We have a group on Slack where we share everything we do. All the cool experiments with how-to guides for you to read so you can try it out for yourself. The brains of the DG STEM TV team are there so you can ask us questions and chat about wonderful sciencey things. Just send an email to us at the address in the comments.
And if you're as excited for episode 3 as I am, then hit like and hit subscribe so you'll be the first to know when it arrives. I can't wait to see you all again. Bye now.